Hello everyone. Today let's learn Pytorch in 20 minutes. In this presentation, I will first introduce Pytorch and then the tensor, and then I will go through the code of a very classic classification problem. Pytorch is an open source machine learning library based on the Torch library, used for applications such as computer vision and natural language processing, primarily developed by Facebook AI Research Lab. It is free and open source software. Although the Python interface is more polished and the primary focus of development, Pytorch also has a C++ interface. Facebook operates both Pytorch and Caffe2, but models defined by the two frameworks were mutually incompatible. The Open Neural Network Exchange, which is also called ONNX project, was created by Facebook and Microsoft in September 2017 for converting models between frameworks. Caffe2 was merged into Pytorch at the end of March 2018. There are several features of Pytorch. First of all, it's easy to use API. It's just like Python. Secondly, it supports Python. It's very similar to NumPy that you can hardly notice the difference. Thirdly, it's dynamic computational graph. Dynamic computational graph in Pytorch, you can use a much more native Python with lots of conditions to adjust training prediction during the actual run. This not only allows you a lot more flexibility, but also better debugging, as error will show up in Python code instead of the compiled version. Here is a comparison between NumPy and Pytorch. You can see that the formats are very similar. You import NumPy here and you import Pytorch here. You define the variables and you initialize x, y, w in learning rate. In the for loop, you first do the forward pass, and then you calculate the loss, and then you print out the loss, and you calculate the gradients, and then you update the weight. Here are some very frequently used classes. Torch is very similar to NumPy, but it supports GPU. Torch autograd. Pytorch uses a method called automatic differentiation. A recorder records what operations have performed, and then it replaces it backward to compute the gradients. This method is especially powerful when building neural networks to save time on one epoch by calculating differentiation of the parameters at the forward pass. Torch autograd will calculate the backward for you so that you don't have to worry about differentiation. Torch autograd makes it easy to define computational graphs and text gradients, but raw autograd can be a bit too low level for defining complex neural networks. This is where the NN module can help. Torch Optim is a module that implements various optimization algorithms used for building neural networks. Most of the commonly used methods are already supported, so there is no need to build them from scratch. Torch Utils provides you the commonly used data loader, trainer, and extra. And here are the frequently used libraries. Torch Vision has some common image processing classification detection models. Torch Text includes the preprocessing for text, tokenization, get-word embeddings, getting entities, and extra. Torch Audio includes speech preprocessing, speech recognition models, and extra. Here are some very useful links, such as the official website, the GitHub, and the API and the tutorials. In the official website, you can see how to download and install Pytorch and Torch Vision. You can simply choose the operation system, the language, the CUDA version, and then you can install to Pytorch. Pytorch defines a class called Tensor to store and operate on homogeneous multidimensional rectangular arrays of numbers. Pytorch tensors are similar to NumPy arrays, but can also be operated on the CUDA-compatible NVIDIA GPU. Pytorch supports various subtypes of tensors. Here, I construct a 5x3 matrix uninitialized, and by printing it out, you can see that X is a tensor. I can also randomly initialize and get the tensor size. By using torch.rand, I can get a randomly initialized tensor, and by using x.size or x.shape, I can get the tensor shape. To get a slice of tensor, it's the same as NumPy. Here I want to get all rows and the second column of the tensor x. A is a tensor with 5 ones, and to convert a tensor to NumPy, I can simply use .numpy to convert it. And there's zero memory cost. It's very efficient. They use the same space, and pointer A and pointer B are pointing to the same location. To convert NumPy to tensor, it's also very easy by using the from NumPy. How do we put a tensor onto a GPU? I create a tensor and its size is 5 times 5. To put it onto GPU, just use .CUDA. And now A is on GPU 0. Similarly, I can also put a model, a ResNet 50, to GPU as well. Why do we want to put tensor and model onto GPU? Because it will be so much faster for training and testing. It speeds up the computation by more than 100 times. Note that CPU tensor and GPU tensor cannot be computed together. So if you see the error message about torch float tensor and torch.CUDA float tensor, it means that your data and model might not be on the same device. To train a Pytorch project, what do we need? The most important thing is the model architecture, such as ResNet, ShuffleNet, AlexNet, and we can also define our own model structure. This is a simple deep neural network. The input is 784 dimension. It's the 28 times 28 image, and the output is 10. It means that there will be 10 labels. You can define the middle layers, which are the hidden layers dimension. We define a class for the model. The first one is the definition of the model. It defines what we need in this model. The first layer input is 784 and the output is 520, and there are 5 fully connected layers in total. After initialization, the model structure will be stored. Then we need to define the forward function. It defines how the information goes through the network. This model is simple. It goes from left to right. We first preprocess the input, a squared image to a 1D vector. Now x in the input, and by using L1x, it means that we feed x into L1. And then we feed the output to ReLU activation function, and so on and so forth. Because it's a classification problem, finally, we will use loss softmax for computing the loss. But do we miss anything? Yes, we miss the backward function, but we don't need to do the calculation ourselves. Pytorch will do the differentiation for us. That's the perfect part of deep learning frameworks. Besides the model, there is another important thing we need to do, which is the data loader. When we process data, we send the data in batches to the model. Pytorch has an API called the data loader, and it will do the job for you. If I have 3 items, A, B, C, we need to shuffle the data first so that the model won't remember the loading sequence. For example, if we know the sequence of questions in a test, you will remember the answer sequence as well, such as ABCD, ABCD. You don't really know how to solve the problem. You remember the answer sequence instead. Well, we don't want our model to learn that, so that's why we shuffle. Data loader is an iterator. Each time, it will feed a batch of data. I is the batch number. Data is what we need to train. In the new version of Pytorch, we don't need variables. We can delete this second line, and it's very easy and efficient for the training pipeline. So what's inside of the data loader? There are several parameters: dataset, batch size, shuffle, number of workers. Number of workers defines how many threads or CPUs to read the data. Shuffle defines if we want to shuffle the data. Usually in training, we want the data to be shuffled, but in validation or test, we don't need shuffle. And then we will need to set it to false in validation test. Batch size defines in each batch how many items will be fed into the model. These parameters are just numbers, but dataset is a bit more complex. We need to define the dataset by ourselves. We inherit the dataset in Pytorch. In init, we define the reading and preprocessing of data, such as downloading or reading a CSV file. In getItem, we define how we read the data according to its index. In length, we get how large is the data length. We can also define some other helper functions in this dataset class. This is a tutorial self-defined dataset class for diabetes data. First, data is stored in a CSV file. We load the data and then read the size of the dataset, and then we convert XY to tensor. When we get item, according to the index, we get the ith image and label. In length, we get the length of the dataset. We usually use Adam SGD for optimizer, and we define the loss function according to the use case. Cross-entropy loss and MNIST loss and triplet margin loss are very frequently used for me. We don't really need to implement them by ourselves, and Pytorch has already defined them. Isn't it just nice? And what's the process of training? We get the data in this batch. We first initialize the gradient to 0 from the previous batch, then we calculate forward. We load the model and feed the data into the model, and then output y. Here, format model data defines the forward. Then we calculate the loss. We don't really know what's inside the backward. Pytorch will take care of it. And then gradient is stored in optimizer. By using optimizer.step, all the parameters get updated. So in total, there are 5 lines. And here is printing out some useful information. Now let's go through a very classic Pytorch classification problem, MNIST classification. Here is the link to GitHub. Okay. So here, it defines the model. Unlike the previously mentioned 5 fully connected layer, it's more complicated. It uses conv layers. So here, it has 2 conv layers, 2 job out, and 2 fully connected layers. And here it defines the forward function. We first feed the input into the conv layer, and then we feed it to ReLU activation function, and another conv layer, another ReLU. And then we use max pooling, and then job out. We then flatten the input to a 1D array, and then we use the fully connected layer, ReLU again, drop out again, and then another fully connected layer. And finally, we use log softmax to compute the loss. And here is the training function. By using model.train, it means that all the gradients can be calculated. It's not frozen. And for each batch, we first load the data, and then we set the optimizer to 0, and we do the forward and calculate the loss, and then go backward, and then the optimizer gets updated. And whenever we need to print out some useful information, we can print them out. So here, I print out the epoch number, the percentage of the data have been loaded, and the loss. If it's dry run, it means that I only run one batch, just to make sure that the code is working well. Test is very similar to train, except that it uses model.eval. It means that the model is frozen, so you cannot calculate the gradient anymore. Here is the main function. You can decide the parameters such as batch size, epoch, learning rate, gamma, and so on and so forth. In here, you use the transformation. You just convert the data into tensor and then normalize the data. And here you define the dataset and data loader. Since MNIST is so commonly used, we don't really need to write the dataset by ourselves. We can use torchvision.dataset.mnist to load the training data and the testing data. And then we get the model, we get the optimizer, we get the LR learning rate scheduler, and then for each epoch, we train and test and then update the learning rate. If we want to save the model, then we use torch.save to save the model. So that's all. Thank you for listening.